things from last time. We were over this graded ring, and we had this L was a line bundle of degree 0 on an elliptic curve, on a cubic curve. And I said we could get this resolution. O minus 2 to the 6, O minus 3 to the 9, O minus 4 cubed. Well, first of all, I referred to this as a non-minimal resolution, which is not quite correct. What I should have said is it's, I can take this line bundle, can correspond to many different modules over this ring, right? And this is coming from the minimal resolution of a module that gives you that line bundle. But it's not sort of the most obvious module. The most obvious module would have one of the two smaller resolutions that we saw earlier. But this one is if we take the obvious module and we surject onto R mod the maximal ideal squared, right? The maximal ideal is x, y, z. And we take the kernel of that. So when we pass from modules to sheaves on Pn, this, because it's supported at the origin, goes away, and these two become the same. And this is coming from the minimal resolution of this kernel rather than the obvious module. So I was wrong to call it a non-minimal resolution, so sorry about that. And then one of you asked if we take if we take, how do we take the minimal resolution on Pn and turn it into a resolution on the hypersurface? What we did was we looked at L minus 3 and the same resolution. And you could have done this with, I just wanted to do something that wasn't, some resolution that wasn't a Koszul complex. So it would be a little bit richer than what we'd been seeing. So this is O minus 5 to the 6, O minus 6 to the 9, O minus 7 cubed. And we want to go back and forth between thinking about modules over this ring, so you can just replace the O with an R, and sheaves on P2. So we said that the map F here is 0, and so if I lift F, then it's, because this is a free resolution when we think about modules over the ring, then it's null homotopic. And you have an exercise with a twisted cubic on a cubic surface, and there you only have a 2-term resolution, and that is actually going to work just fine. But I was a little bit lazy or sloppy, and well, here's, so I said you could get a matrix factorization in the following way. 0 from L, the same thing. And then here, I'm going to put the second row of that resolution, O minus 6 to the 9, O minus 7 cubed. And here are my D's, and here are my H's. And then I need to continue. So O minus 8 to the 6, and so on. O minus 9 to the 9, and so on. So here's H. So DH plus HD is F. And so I said we get a matrix factorization, that if I do this and then this, I get a matrix factorization. But in fact, I should have been more careful, because if I go from here to there, this gives a matrix factorization if h squared is 0. Right? And in many of my favorite examples, you can cook it up so that h squared is 0 without too much trouble, especially if you started with like a linear space on a quadric and you did a Koszul complex. You can choose your h's to have h squared is 0 by sort of being another Koszul complex kind of thing. But in general, h squared is not 0, but h squared is a chain map, and it gives an element of x2, or not x2, but x minus 2 of the module with itself, or I guess in this case of L minus 6, well, or the module associated to L minus 6 with L. But of course, there are no negative x's between modules over a ring, and so, and therefore it's null homotopic. Right? So to do this properly, you need to choose a null homotopy of h squared and use that to fix this thing further. So choose the null homotopy and repair this matrix factorization. And you can imagine, as this minimal free resolution gets longer and longer and longer, you're going to have to choose more and more null homotopies to repair this. So that's a fiddly piece that I glossed over last time. But in the exercise, which was with the twisted cubic in a cubic surface, let's twist cubic C in a cubic surface S in P3. And I chose this one is close to my heart because it's important in constructing the Lane et al.'s hyperkähler eightfold that's made from a cubic fourfold. So it's not just a made-up example. It really comes up somewhere, but I don't want to get into that. We had this. OC came from OP3, from OP3 of minus 2 cubed, from OP3 of minus 3 squared. This was the minimal resolution. And their h squared really is 0 because there's just nowhere for h squared to go. And so the minimal resolution looks like this. We would have OC from, this was the minimal resolution on P3 of the curve. The minimal resolution on S of the curve will look like this, OS of minus 2 cubed from OS of minus 3 cubed, right? Because it'll be these two plus this one minus 3 from OS of minus 5 squared cubed, OS minus 6 cubed. And one of you asked, how do we know that that thing is exact? So, and I thought some others would like to hear the answer. Why is it exact? So, well, we have these pair of matrices. We've cooked up these pair of matrices using DH plus HD. So on P2, we have, well, okay, so it's exact. I want to explain why it's exact out here in the stable range. Right, we have a pair of matrices. Let's see, O minus 5, O P2 minus 5 cubed to O P2 of minus 3 cubed. Maybe this one is N and this one is m OP2 of minus 2 cubed with mn is nm is, f times the identity, where f is our cubic polynomial. And so you want to restrict to C, and now f equals 0. And so the fact is, now the kernel of m restricted to C is the image of n restricted to C, and vice versa. And this was this same argument that I went through, where you take a column vector and then you lift it to the big ring, and if it was killed by m on C, then on the big ring, right? This whole thing we went through, right? If m times a vector is 0, then m v tilde is f times some w, which is mn times w. So we can cancel the m's and say v is n times w bar. This argument that we've gone through a couple times. But it's worth pointing out that saying that this thing is a matrix factorization on P2 says that this thing is exact on the curve. So does that answer your question? Great. One more thing. So that exercise 2 you should still not do, because while it's true that we've gotten a family of matrix factorizations that's parametrizing all degree 0 line bundles, it's just not true that it's homotopy equivalent to the smaller resolution. So I really did need the other approach that I didn't give you. So maybe I'll give you that later. But this matrix factorization is really not homotopy equivalent to the 3x3 one or the 1x1 guy, because you can tell if this has rank 1, then this kernel has rank 5, and this kernel has rank 4, and none of those are, so this co-kernel has rank 5, and this co-kernel has rank 4, and they're just not the same. They're related, but by some interesting spherical twist, but they're not the same. So sorry about that. Okay. So I want to talk about matrix factorizations in general and making a DG category of them. Right. And so X, so definition of a Landau-Ginzburg model. So we're gonna pretend to be doing physics for 1 second. Ginzburg or LG model. X is going to be, let's say it's smooth. Well, it's going to be a scheme or a stack. And if you're afraid of stacks, that's fine. I'm also afraid of stacks. You'll see in the examples what sort of very mild stacks we're interested in. We need a copy of, it's called R charge. So C star is going to act on X. So this is going to be over C. You could do it over other fields, but let's be over C. C star acts on X, and -1 needs to act trivially. And then we need a function, W, is going to be a function, and it needs to be C star. Well, I'm going to label this C star R because there will be other C stars later. Oh, by the way, was it? I assume you all figured out, but of course C star is just the group C minus. Right? In case anyone was upset about that, it's sometimes denoted C cross. It's for Ed's lecture yesterday. So it's going to be C star R equivariant, invariant, well, equivariant of weight 2. And W is going to be, this function W is going to be called the superpotential. And I think, but I'm not sure, that W is chosen because it's the letter after V, which is often used for potential in classical mechanics, especially in electrical potential where V stands for voltage. But I'm not certain about that. Yeah, it's a section of OX. Well, C star are, if I act, right, I'm just saying for lambda in C star R, I'm just saying that lambda acting on W is lambda squared W. You'll see an example in just a second. So our 0th example, yes? The R is just to distinguish it from other tori that might come along later. It's just C star. Because soon X will be some affine space or some open subset of affine space, mod some torus. And I want to distinguish between that torus and this one. Right, so examples. So first of all, we could take X to be just a scheme. We could take C star acts trivially, and W equals 0. And then, with any luck, we'll recover just the derived category of X as the category of matrix factorizations of 0. One, I could take X to be C2 with coordinates X and P, and C this this R charge is going to act with weight 0 on X and weight 2 on P. So there's a little asymmetry there. Yeah, X and P are the coordinates. So the C star is rescaling these fibers with weight 2. And I'm going to take W to be X times P. Right, so that's a function of weight 2. Or more generally, I suppose you could, yeah. So more generally, and we'll end up finding that the derived, well, the category of matrix factorizations on this is equivalent to a point. That's sort of the only interesting one is X times P. So maybe this is 1A, or well, we'll call it 2. If I have some vector bundle, E, a vector bundle, and you could think, for example, the total space of O minus 3 over P2 will be one of our favorite ones. And if S, a section of the dual vector bundle, so in that example, it's a cubic polynomial. This determines a function on the total space of E, right? If I think of S as a map from E to OB, a map of sheaves over B from E to OB, it then determines a function on the total space of E. Right. I mean, well, yeah. I'm not sure how much to say about this. You do want to think this through. And one way, yeah, is linear on the fibers, right? S is linear on the for each fiber you get a linear form. It varies from fiber to fiber, but that gives you a function. So think about that and ask about it if you have questions. And I'm going to call this function W. And we're going to let C star R act on X, which is going to be the total space of E. It's going to act with weight 2 on the fibers. Right, so here's X. Here's the total space of E. You know, maybe X is a bit bigger, and we're just rescaling the fibers with weight 2. So of course -1 does nothing. And if you think about it, because this function W was linear on the fibers, now it has weight 2 with respect to that C star R thing. And we'll find eventually matrix factorizations of the derived category of matrix I'll write it. The derived category of X W that we'll eventually define is the derived category of just the locus S equals 0 inside of X, inside of B. So this will be our final form of Knurrer. Well, we'll probably only prove it if S is regular. Oh, sorry. Assuming this is if the codimension of S equals 0 is the same as the rank of E. So regular in that sense. I don't mind if the 0 locus is smooth or is singular, but I do want it to be the right dimension. And B should probably be smooth. So in this example, we'll cook up some category of matrix factorizations on this total space that's equivalent to the derived category of the cubic curve. And our third and for now final example is that X is going to be C to the N mod the cyclic group ZD, where if I take some, so this is acting in the obvious way. Right, so if I have some C in ZD, thought of as a root of unity, then C acting on x1 up to xn is cx1, cxn. And I want to take the stack. So I hear at least half the audience being worried. But since we're only interested in sheaves on X, it's enough to know that sheaves on this global quotient stack are the same as equivariant sheaves excuse me, on Cn. And now I'm going to annoy you further. The R charge is going to act on X with weight 2 over d on each coordinate. Which I agree is worrisome. Like, what does it mean to act on a stack? And we'll find that the derived category, and W will just be a degree d polynomial. So matrix factorizations of this X and this W will be equivalent to the category of matrix factorizations from yesterday. The Orlov thing where you take pairs of vector bundles, sums of line bundles on Pn and you go to town eventually. So I want to revisit this example in a minute, and in particular say something to make you feel better about that 2 over d that probably has you upset. But before we go on with that, let's say a matrix factorization. So given, if we fix an LG model, so a matrix factorization consists of a vector bundle E on, sorry, this E has nothing to do with that E, on X, well, a C star R equivariant vector bundle E on X and a map D from E to E shifted by 1, where shifted by 1, this means change the C star R action, right? O shifted by 1 is just OX, where OX is OX with C star, the R charge acting with weight 1 on the fibers, as opposed to usual OX, where C star R won't act on the fibers. It'll just move them around. Such that, take my jacket off. Such that D squared is W times the identity on E. Right? Remember, W is a section of is a section of OX of 2. Right? If I've introduced this notion square brackets for changing the C star action, then rather than write all this business, it's maybe better to say it that way. Okay, so let's try to make contact with and I'll say a sheafy matrix factorization, or sometimes a curved DG sheaf is the same, but with a sheaf F that's not locally free. Or that need not be. So we will eventually be happy to consider matrix factorizations not using vector bundles but using sheaves. But there's more work in setting up the derived category of these things. So let's have some examples. Well, remember example 0 was X is a scheme over C. The R charge acts trivially. And therefore, an equivariant bundle or sheaf is just the same as a graded one. Or sheaf. Right, so F is just the direct sum over all I and Z of Fi. You break the thing into weight spaces for this C star R action, where C star R acts on Fi with weight I. D squared is W, and we said W is 0, and D is a map of weight 1, so we just have a complex of sheaves. Just a complex of sheaves. Right, so there's absolutely nothing mysterious about that example. In example 1 that I foolishly erased, 1 was we had C2 with coordinates x and p, and R charges were 0 and 2, and W was xp. I'm thinking of the map O. I want to think about that matrix factorization. So how do we formalize it in this context? I want to take E to be O plus O shifted by minus 1. And so E shifted by 1 is OX of 1 plus O x. And my matrix D is going to be XP, if I haven't messed up too badly. Right, X goes from there to there. That's fine. And P goes from there to there. And so D squared is XP. XP is W times 1. I want to talk about example 2 more tomorrow. Let me skip ahead to example 3. So 3, here's a better way to formulate 3. Let's take, well, instead of C3 mod Z3 and then all the other window dressing. Let's consider, 'cause it's hard to say what a C star action on that thing really means, because essentially we've chosen the wrong affine chart for that scheme. Let's consider C3 cross C star with coordinates x, y, z here and p there. Mod C star, this acting with weights 1, 1, 1, and minus 3. So you can see, why are these the same stack? Because if I use this C star to set p equals 1, right, then every point in this space is in an orbit with p equals 1, but p equals 1 has some stabilizer, right, because C star is acting on p with weight minus 3. And so I could set p equals 1 and get rid of it, but then it'll have some stabilizer, and the residual stabilizer, so stabilizer of p equals 1 is z mod 3, and it acts on x, y, z via cube roots of 1. Okay, so exercise, think about that. And now I'm going to let my R charge act more pleasantly in this chart. Is going to act with weights 0, 0, 0, and 2. And now this is okay. These commute. Really, a group action on a stack, if your stack is a global quotient, it should be the two groups act in a way that commutes. And here it's really painful to describe, but up here it's much nicer. So we're done. And let's take one of our examples from yesterday and get a matrix factorization on here. How am I doing for time? So example from yesterday. So I claim that matrix factorizations in the way I've set it up today on this LG model are the same as the category that we considered yesterday. So let's see an example. Remember, we had an elliptic curve C, and we had a point x equals y equals 0. Right, and so we wrote f to be x q1 plus y q2. And we considered this matrix factorization. O minus 1 squared came from O minus 2 plus O minus 3 came from O minus 4 squared. Here we had M, which was x minus y q2 q1. The determinant of that is f. And n was q1x minus q2y. Switch those. So in today's formalism, I'm going to take E. Let's see if we can do this right on the first try. I want to take O minus 1 squared plus O minus 2 plus O minus 3 shifted by 1. So these, remember the square brackets refers to C star, and the round brackets to the other. This one is the R charge to the other C star. So E shifted by 1. And I want you to notice that P is a non-vanishing section of O of minus 3 shifted by 2. This is a non-vanishing section. So in fact, it gives an isomorphism from O minus 3, from O of 3 to O shifted by 2. So E of 1 is O minus 1 squared, or O, plus O minus 2 plus O minus 3 shifted by 2. And now how can these go? So D, from there to there, here I'm going to put M. That's legit. And there I'm going to put P times N, right? Because I could also. I feel like you can think of. Oh, I forgot to tell you. So W is going to be P times F. Right, this is going to be invariant with respect to this C star. And it's going to be weight 2. Weight 2 with respect to the other C star. So D D is this matrix, M, Pn, and D squared is Pmn, Pmn, Pnm, which is Pf, which is W. So this seems like a painful way to rephrase something that was more or less clear yesterday, but I claim this is actually going to be a worthwhile way to set things up. Okay. Here's another example, a Sheafy example, in the same LG model. So here's a Sheafy example on the same LG model. And actually it'll be even more convenient to view it as being on C3 mod, well, Z3. We just take the well, on on C3, right, we said that this was, how can I do it? What's the smart way to do it? Here we had the minimal resolution of some line bundle L. So L was OC of minus P, right? It was the ideal sheaf of P, because right? That's how we got this minimal, we got this complex. Take the sheaf associated to the C XYZ module from OC of minus P. Minus the, I want to distinguish, okay. This P is not related to that P. Right, and I want to move that over to C3 mod Z3, if you like. But the point is that, so I'm going to take, let's call that sheaf F. It's locally free away from the origin of C3, right? I'm going to take the sheafy matrix factorization F, and then D equal, like just F in degree 0, and D is 0. And the point is that W, which is F, right, F acting on 1F is the same as 0 acting on 1F. So indeed, D squared is F. And ultimately, I'm not sure that I'm going to get to it in this hour, but I do want to convince you that with whatever sort of killing of quasi-isomorphisms we do, this becomes isomorphic to that. So the point of this sheafy matrix factorization or curved DG sheaf business is that we can consider both good old matrix factorizations of W using vector bundles, or we can consider just sheaves supported on the locus where W is 0, and they'll become, and we can sort of move back and forth between these as we like. It's like if you were going to set up the derived category, you could do it entirely with vector bundles. If you're on a smooth space, right, everything has a finite resolution by vector bundles. But it wouldn't actually be very convenient to work in that category and not have access to sheaves. So given two possibly sheafy matrix factorizations E and F, we're going to make this into a DG category. So define the Hom complex from E to F. So now we're on a general LG model, and this is going to be a sheaf Hom complex to be the sum of over all I and Z of sheaf Hom from E to F shifted by I. And if I have some phi here, if I have some phi which is given in components by some phi i's, then I'm going to declare d phi is going to be what you expect. It's going to be, well, let me get the signs right. It's going to be dE after phi plus minus 1 to the I times phi after dF. So exactly what we did before. A slightly funny thing happens. Even though on E and F d squared was W, this Hom complex is going to be an honest complex. So d squared phi, right, this is going to be dE, oh wait, have I, yeah, that's all right. This is dE squared phi plus minus 1 to the I plus 1 dE phi dF. Hey, have I got my E's and F's on the wrong side? Yes, I absolutely do. Right. Phi I goes from E to F. Help me get this straight. Yeah, I've switched my E and F when I didn't mean to. Sorry. dF phi dE. Plus, and there should have been i's there, plus minus 1 to the I dF phi dE plus minus 1 to the 2I plus 1 of phi dF squared. If I've done things correctly. So these two cancel in the middle. But this is W times phi I, and this is minus W times phi I. So it was worth doing this once we get 0. Right, so even though d squared was not 0, nonetheless, so d squared was not 0 on E and F. Nonetheless, d squared is 0 on the Hom complex. Okay. So our first attempt at a DG category. So if X is affine, right? Make a DG category whose objects are matrix factorizations, right? With the E's are locally free. And straight Hom is just H0 of the sheaf Hom complex. And this will actually be the right thing for two reasons. First of all, because E at least was locally free. Because these were both locally free, there's no sheaf, like this curly Hom does not have to be derived. And because X is affine, H0 doesn't have to be derived. Right, so that will be, and this, right, and then taking H0 of this will give you exactly chain complexes mod chain homotopies. It will give you the sort of thing we considered yesterday. If X is not affine, there are two things we could do. We could keep our objects as bundly matrix factorizations. And we could replace H0 of this Hom complex with either a check or Dolbeau. I guess I should capitalize his name. Dolbeau model of R gamma sheaf Hom. So Sasha talked to you a little bit on Friday about how you could, if you have a finite affine open cover with all the intersections being all right, then you can make a check complex to compute the cohomology to make your DG category. So you could do that, or you could do, since we're over C, you could do it with smooth differential forms, and that would be one way to go about it. See, I'm out of time, so I'm just going to say we'll take this up next time. Or we could allow sheafy matrix factorizations. And, well, we could even allow quasi-coherent sheafy matrix factorization. So maybe we have complexes of injectives around or something. And we could invert quasi-isomorphisms. But the issue, which we'll take up next time, I guess, is that quasi-isomorphisms doesn't make any sense. Right? Because like dE squared is not 0, it's W. So you can't talk about the cohomology of E and the cohomology of F. And whether it induces an isomorphism on cohomology. But instead, you force short exact sequences 0 to E1 to E2 to E3 to 0. Well, maybe I can call this F to be exact. Well, obviously, I have to explain what the hell I'm talking about. So we want to do something where a short exact sequence, let's say it this way. I force short exact sequences to turn into exact triangles. So we'll take that up next time. And in lieu of exercises today, we are going to take a picture. So Tracy is somewhere. I guess we're supposed to go find her, and then we're going to all go out front and get photographed.